The cosmos hides a vast population of celestial misfits. These are substellar objects, cosmic bodies that are not quite stars and not quite planets, and they are rewriting the rules of our galaxy. By the end of this, you will understand the invisible architecture of space and the true nature of the dark wanderers between the stars. We will explore the critical line that divides them, a nuclear process few have heard of, and ask what kind of weather happens on a world with no sun. What do you believe is waiting for us in that profound darkness? The line between a star and a planet is not as sharp as you might think. A substellar object is at its core a cosmic underachiever. It is a celestial body that simply does not have enough mass to ignite and sustain the primary nuclear reaction that defines a true star, which is the fusion of ordinary hydrogen into helium in its core. This fundamental lack of power places them in a fascinating gray zone. The most well-known members of this category are brown dwarfs, those failed stars that glow dimly with leftover heat, and the more mysterious free-floating planetary mass objects, often called rogue planets, which wander the galaxy unattached to any sun. What truly binds this odd family together is a specific critical threshold of mass. This is the deuterium burning limit. It sits at approximately 13 times the mass of our own planet Jupiter. Any object below this limit cannot even fuse deuterium, which is a heavy isotope of hydrogen, in its core. This means these objects are not massive enough to be stars, yet many are too massive, too hot, and formed in too star-like a manner to fit our classic definition of a planet. They exist in their own unique astrophysical category, a population of cosmic in-betweens that challenge our very systems of classification. This dividing line is not just a number. It is a fundamental shift in a celestial body's internal engine. To understand it, we need to talk about deuterium. Think of a regular hydrogen atom as a simple, lightweight sphere. A deuterium atom is its slightly heavier cousin with an extra particle in its nucleus. That small difference makes all the difference in the cosmos. Fusing these heavier atoms together requires far less extreme pressure and heat than fusing ordinary hydrogen. So while a true star needs immense mass to crush its core and ignite a roaring, self-sustaining hydrogen furnace, a substellar object can, if it is heavy enough, light a much smaller and shorter-lived nuclear spark. This is deuterium burning. It is more like a pilot light flickering in a vast, dark chamber, not the full inferno of a star. The mass required to strike that spark is around 13 times the mass of Jupiter. At that critical threshold, the gravitational squeeze inside the object finally generates enough pressure and temperature to force deuterium nuclei to fuse. Any object above this line capable of that brief nuclear fire earns the classification of a brown dwarf. It is a failed star, but one with a faint internal nuclear history. Anything below that 13 Jupiter mass limit lacks the gravitational might to ignite even this modest process. It is, from a nuclear perspective, completely inert. These are the substellar objects mass below deuterium burning. They generate no new energy from fusion at all, only glowing with the fading warmth of their own violent birth and the slow, relentless crush of gravity. This simple, silent distinction creates two entirely different cosmic destinies from what is, in many ways, the same raw material. Above that 13 Jupiter mass line, the cosmic landscape is ruled by the brown dwarfs. These are the failed stars, the primary residents of the mass range just above the deuterium limit. They form in the same way stars do, from the gravitational collapse of vast clouds of gas and dust. But in their case, the clouds simply did not have enough raw material. It is like trying to build a roaring bonfire with only a handful of kindling. The collapse creates a dense, hot ball, but one without the critical mass needed to light the main hydrogen fusion engine. What you get instead is a substellar object that briefly ignites its deuterium fuel, a faint nuclear flicker that may last only a few million years before sputtering out. After that, a brown dwarf has no internal power source. It simply glows with the residual heat of its violent birth, slowly radiating that energy away into the frigid darkness of space over billions of years. This slow cooling process means brown dwarfs are best seen in infrared light, as they emit a deep, warm glow invisible to our eyes. Their atmospheres are places of profound and alien weather. With temperatures ranging from that of a hot oven to a cool summer day, these objects can host clouds not of water, but of molten iron and silicate minerals, raining liquid rock or hot sand. The discovery of systems like Lumen 16, the closest known brown dwarfs to Earth just over 6 light-years away, was a revolution. It proved these objects were not rare theoretical curiosities, but a vast hidden population. They forced astronomers to rewrite the book on stellar formation, revealing that the universe produces far more of these underachievers than it does brilliant suns like our own. But what about the objects that fall below even that faint nuclear spark? Below the 13 Jupiter mass line lies a realm of profound darkness, occupied by the true nomads of the galaxy. These are the free-floating planetary mass objects, often called rogue planets or sub-brown dwarfs. They are worlds without suns, celestial bodies that either formed in lonely isolation from the same collapsing clouds that make stars, or were violently ejected from their young planetary systems by gravitational chaos. Imagine a planet like Jupiter, but born alone in deep space or hurled from its cradle into the endless night. These objects possess no internal fusion, not even the brief deuterium flicker of a brown dwarf. Their only warmth is the fading ember of their formation, and over time they become colder than the coldest ice in our solar system, drifting through the interstellar void in perpetual twilight. Finding these dark wanderers is one of astronomy's greatest challenges. They emit almost no light of their own, especially as they age and cool. To spot them, scientists rely on clever cosmic tricks. One method is gravitational microlensing. When a rogue planet drifts precisely between Earth and a distant star, its gravity acts as a tiny lens, bending and magnifying the star's light for a brief period. That telltale flash and fade in the data is the signature of a hidden, massive object. The other primary method is persistent, painstaking infrared imaging, searching for the faintest of warm glows against the absolute cold of space. Projects like the James Webb Space Telescope are now peering into nearby star-forming regions, hoping to catch the dim infrared signature of these young, still warm, free-floating worlds. The existence and potential abundance of these rogue planets forces us to rethink the cosmic census. For every star system with planets orbiting in an orderly fashion, there may be countless more worlds ejected into the darkness. Some estimates suggest there could be billions, even trillions, of these nomads wandering the Milky Way alone, far outnumbering the stars. This changes our understanding of planetary system dynamics dramatically. It shows that the early lives of solar systems are often violent and unstable, a gravitational game of pinball where many worlds are lost to the void. But it also raises a tantalizing possibility. If a rogue planet retained a thick, insulating atmosphere and internal geothermal heat, could it harbor a subsurface ocean, a pocket of liquid water and potential chemistry adrift between the stars? The idea transforms these dark, frozen worlds from mere cosmic debris into potential havens, lonely arcs sailing the galactic sea. Their sheer numbers suggest that life, if it can arise in such isolation, might be far more widespread and stranger than we ever dreamed. Finding these cosmic ghosts requires us to see the universe in a different light, quite literally. Our eyes and traditional optical telescopes are nearly useless for this hunt. These instruments are designed to see the brilliant glare of stars, the reflected sunlight from planets, but not the faint, deep warmth of a cooling, sunless object. A rogue planet or an old brown dwarf is essentially invisible in visible light. It emits no significant light of its own in that spectrum, and with no nearby star to illuminate it, it vanishes into the blackness of space. To find them, astronomers must become detectives of the infrared, the domain of heat. Every object with a temperature above absolute zero emits infrared radiation. It is the same warmth you feel from a radiator or a cup of coffee. For these cold substellar objects, their entire existence is broadcast as a faint infrared whisper. Space-based observatories like the Wide Field Infrared Survey Explorer, or WISE, and the now-retired Spitzer Space Telescope have been instrumental in this search. They conducted vast, all-sky surveys, scanning the heavens for those subtle points of infrared warmth that optical surveys missed. These missions have catalogued thousands of brown dwarfs and hinted at the presence of even colder, planetary mass objects by their unique infrared colors. But to go from a fuzzy infrared dot to a detailed world, we need more than a survey. We need a close-up. This is where the most powerful tools come into play. Direct imaging is the ultimate goal. It means taking an actual picture of the object itself, separating its incredibly faint glow from the overwhelming light of any nearby stars. This is a monumental technical challenge, like trying to photograph a firefly sitting next to a giant searchlight. Ground-based telescopes equipped with advanced adaptive optics use lasers to measure atmospheric turbulence and deform their mirrors thousands of times per second to cancel out the blurring effect of Earth's atmosphere, creating a crystal-clear image. And from above the atmosphere, the James Webb Space Telescope is a game-changer. Its immense mirror and supremely sensitive infrared instruments can directly image young, still warm rogue planets in nearby stellar nurseries, studying them in unprecedented detail. Once we have that image, the real science begins. Astronomers use a technique called spectroscopy. They take the faint infrared light from the object and spread it out into a rainbow or a spectrum. This spectrum is not just a bar of color. It is a unique fingerprint filled with dark lines and bright bands that act as a chemical barcode. By reading this barcode, scientists can determine the object's temperature, estimate its mass, and even identify the molecules swirling in its alien atmosphere. They can find the signatures of methane, water vapor, or those strange clouds of molten silicate or iron droplets. But what about the oldest, coldest rogue planets that have radiated away almost all their heat? For these, even the most sensitive infrared telescopes may fail. Their discovery relies on a cosmic coincidence called gravitational microlensing. If a dark, massive object like a rogue planet passes directly between Earth and a distant, bright star, its gravity will act as a tiny lens. It bends and focuses the star's light, causing the star to temporarily appear brighter to us. This brightening follows a very specific pattern that reveals the lensing object's mass and distance. It is a fleeting event, lasting days or even just hours, but it is one of the only ways to detect the truly cold, ancient population of nomads drifting silently through the galactic dark. Each of these techniques reveals a different slice of this hidden population, building a census of the cosmos we never knew existed. The atmospheres of these failed stars are laboratories of alien chemistry. While a brown dwarf cannot sustain true starlight, its interior still churns with immense heat, and its atmosphere becomes a dynamic, layered cauldron where familiar elements behave in utterly unfamiliar ways. Temperature is the master artist here, painting wildly different scenes across the mass and age spectrum of these objects. In the warmer, younger brown dwarfs classified as L-dwarfs, temperatures can soar high enough to vaporize rock. Here, high in the atmosphere, clouds do not form from water vapor. Instead, they condense from vapors of silicate minerals, the same stuff that makes up sand and glass on Earth. Imagine a sky filled not with fluffy white cumulus, but with swirling, oppressive clouds of molten sand and droplets of liquid iron, raining a scorching metallic drizzle into the depths below. As we move to cooler T-dwarfs, the temperature drops enough for different chemistry to take stage. Methane, a gas we associate with distant ice giants like Neptune, becomes a dominant feature in their spectra, giving them a distinct chemical signature. And in the coldest known class, the white dwarfs, with temperatures dipping below even that of a human oven, other exotic compounds like ammonia or water vapor might condense into ice clouds. The weather on these worlds is anything but gentle. Observations suggest these atmospheres are roiled by planet-scale storms and powerful jet streams. The clouds are not static, they patch, clear, and reform in dynamic global patterns, driven by the intense internal heat trying to escape and the object's rapid rotation. Some brown dwarfs, like the famous Lumen 16 binary system, show clear, direct evidence of these cloud bands and storm systems when imaged over time. This makes them not just curiosities, but incredibly valuable analogies. A hot, young gas giant exoplanet orbiting close to its star has an atmosphere physically very similar to an isolated, warm brown dwarf. By studying the complex chemistry and violent meteorology we can see directly on these free-floating objects, we gain a template, a Rosetta Stone, for interpreting the faint, blurry atmospheric data we collect from exoplanets light years away. The brown dwarf becomes a controlled experiment, a giant planet removed from the blinding glare of a star, allowing us to decode the atmospheric alchemy that might be happening on countless worlds across the galaxy. This simple division between brown dwarf and rogue planet, however, is where the cosmic map gets blurry. The 13 Jupiter mass line, while clear in physics, has become a frontier of fierce debate in astronomy. The core of the controversy is this: should we classify celestial objects by what they are made of and what they can do, or by how they were born? The physics-based definition draws that bright line at deuterium burning. Anything above it fuses, however briefly, and is a substellar object called a brown dwarf. Anything below it does not and is a planetary mass object. This seems clean and objective, but nature is rarely so tidy. The problem arises because we now know objects can form in two very different ways that lead to the same final mass. A ball of gas could collapse directly from an interstellar cloud, a star-like formation, resulting in a free-floating object of, say, 10 Jupiter masses. By the physics definition, that is a rogue planet, a substellar object mass below deuterium burning. Yet, in another solar system, a gas giant planet could form in a disk around a young star and then be catastrophically ejected by gravitational forces. That ejected world could also weigh 10 Jupiter masses. It is, by formation, a planet. So now we have two objects identical in mass, temperature, and composition, one a failed star and one an exiled planet. Are they the same class of object or different? This is the heart of the planetary mass brown dwarf debate. It reveals a fundamental tension in how we understand the cosmos. Do we care more about an object's intrinsic properties or its origin story? Proponents of a formation-based system argue that history matters. They say calling both objects the same thing ignores the profoundly different pathways that created them, pathways that tell us about the diversity of processes in the universe. Others push for the clarity of the physics-based definition, pointing out that we cannot always know how an isolated object formed. We can measure its mass, its spectrum, its temperature, but its birth is often a lost piece of history. This ambiguity is most intense right in that messy zone near the limit itself, from perhaps 5 to 15 Jupiter masses. Here, in what some call the mass gap, objects blur together. A 12 Jupiter mass object that cannot quite fuse deuterium might look and behave almost identically to a 14 Jupiter mass object that can for a short time. This has led some scientists to propose we should think not in rigid boxes but in a continuum. Imagine a spectrum. On one end you have classic stars. On the other you have classic rocky planets like Earth. In between stretches a vast and varied family of substellar objects, with brown dwarfs and large gas giants and rogue planets all as members of a connected sequence. Their properties, like temperature, chemistry, and weather, change smoothly with mass and age, not in sudden jumps at arbitrary lines. This ongoing classification struggle is far more than academic bickering. It is a sign of a healthy, evolving science confronting a universe more complex and wondrous than our old categories allowed. Every time we argue about where to draw the line, we are really refining our questions about how everything in the cosmos comes to be. The debate over classification forces us back to the very beginning, to the moment these objects are born. Their origins are written in two distinct cosmic scripts, and each tells a different story about chaos and chance in the galaxy. The first pathway is a solitary, star-like birth. In the cold, dense nurseries of interstellar space, not every collapsing cloud of gas and dust is destined to become a sun. Sometimes a small, isolated knot of material, too meager to ignite the stellar furnace, pulls itself together under its own gravity. This direct collapse creates a free-floating substellar object from the very start. It forms alone, a celestial-only child in the vast dark with no star to call home. Its composition is typically rich in the primordial gases of the cloud, similar to that of a star. This is the classic formation story for most brown dwarfs, and we suspect for many of the larger rogue planets we find drifting between the stars. They are not failed planets, but rather stars that never truly got started. The second pathway is one of violence and exile. Picture a young solar system, a whirlpool of gas and dust swirling around a newborn star. Within that disk, planets are coalescing. Giant worlds of gas, many times the mass of Jupiter, take shape, but this early era is a gravitational free-for-all. As these massive young planets jockey for position, their orbits can become unstable. In a cosmic game of pinball, one can be slingshotted inward while another is hurled outward, completely ejected from the system. This ejected world, now a rogue planet, is cast adrift. Its formation was planet-like, born in a disk, but its destiny is one of eternal solitude. The evidence for this dramatic process is written in the oddities of our own galactic neighborhood. Astronomers have observed hypervelocity stars flung from the center of the Milky Way, and computer simulations consistently show that young planetary systems are incredibly efficient at ejecting their own members. It is not a bug in the system, it is a feature. For every stable solar system like ours, there may be countless others that violently expel one or more of their giant worlds into the interstellar deep. So which story is the true one? The answer, remarkably, is likely both. Our galaxy is not choosing a single formation method, it is using every tool in the box. This duality is what creates the fascinating ambiguity in that mass gap we discussed earlier. We could have two objects, each with a mass of 10 Jupiters, drifting through the same region of space. One formed alone from a cloud, a substellar object from birth. The other was born in the warmth of a protoplanetary disk and then violently orphaned. To our telescopes, they might look nearly identical, cold and faint, but their internal chemistry could hold subtle clues, fingerprints of their origins. An object born from direct collapse might have a different mix of elements compared to one that formed in the crowded, processed environment of a planetary disk. Untangling those signatures is a primary goal for observatories like the James Webb Space Telescope. This means the population of dark wanderers is not a single, homogeneous group. It is a mixed diaspora, a collection of cosmic orphans from two very different kinds of families. Some were always alone, others remember the warmth of a sun. That unresolved question of origin is precisely why we needed a new kind of eye in the sky. For decades, the faint infrared whispers of the coldest substellar objects were just at the edge, or even beyond what our telescopes could clearly hear. The James Webb Space Telescope has changed the conversation entirely. It is not merely an upgrade, it is a revolution in our ability to see the dark. Its primary mission is to peer into the infrared universe with a sensitivity and resolution that dwarfs anything that came before. Think of it as moving from listening to a distant radio station through static to hearing a symphony in perfect, crystal-clear detail. This power is tailor-made for the realm of substellar objects mass below deuterium burning. Where the Hubble Space Telescope saw mostly the bright light of stars, Webb sees the deep, warm glow of the cosmos. Its massive gold-coated mirror collects far more of that faint infrared light, and its suite of instruments, kept at temperatures colder than deep space itself, can analyze it without being blinded by their own heat. This allows Webb to do two critical things that were nearly impossible before: direct imaging and detailed spectroscopy of these cold, faint wanderers. Instead of inferring their existence from microlensing statistics or fuzzy infrared dots, Webb can now take actual portraits of young, free-floating planetary mass objects in nearby stellar nurseries like the Orion Nebula. It can separate their dim glow from the bright background with stunning clarity, giving us our first true look at their shapes and immediate environments. But the real magic happens with spectroscopy. Webb does not just take a picture, it takes a fingerprint. By spreading the infrared light from a brown dwarf or rogue planet candidate into a spectrum, it reveals a detailed barcode of its atmosphere. Every dip and peak in that barcode corresponds to a specific molecule: water vapor, methane, carbon monoxide, even the signatures of those exotic silicate or iron clouds. Early results have been breathtaking. Webb has already delivered the most detailed spectra ever taken of brown dwarfs in our cosmic backyard, precisely measuring their temperatures and chemical compositions, and confirming the presence of complex, patchy cloud structures. It has peered into star-forming regions and identified new, incredibly faint objects with masses likely in the range of just a few Jupiters, strong candidates for free-floating planets. Each new dataset is like receiving a detailed weather report from a world with no sun. This flood of pristine information is the key to settling those fierce classification debates. By comparing the atmospheric chemistry of a free-floating 10 Jupiter mass object to that of a known, orbiting gas giant exoplanet, scientists can search for the subtle chemical fingerprints that might betray its origin, whether it formed like a star or like a planet. Webb's census of objects in stellar nurseries will give us a much clearer statistical picture, revealing just how many of these substellar bodies are born in solitude versus how many are ejected later. In essence, Webb is turning the faint whispers of the dark cosmos into a clear, loud conversation, one that will ultimately map the true, hidden population of the galaxy and rewrite the story of how celestial underachievers are born. The search for these cosmic nomads is not confined to professional observatories. It has spilled out into living rooms and home offices around the globe, powered by the most powerful pattern recognition tool in existence, the human eye. This is the world of citizen science, where anyone with curiosity and an internet connection can help write the next chapter of astronomy. One of the most successful projects in this field is called Backyard World's Planet 9. The name itself hints at its dual mission: to find our solar system's hypothetical ninth planet, and to catalog the nearby brown dwarfs and rogue planets that populate our galactic neighborhood. The principle is elegantly simple, but the task is monumental. Space telescopes like the Wide Field Infrared Survey Explorer have mapped the entire sky, not once, but multiple times over several years. This creates a kind of time-lapse movie of the cosmos. Within that movie, stars and galaxies are essentially fixed points, but nearby substellar objects, because they are so close to us, show a subtle movement against the more distant background. This tiny shift in position, called proper motion, is the telltale sign of a potential discovery. The challenge is that the datasets are vast, containing hundreds of millions of points of light. Even the most advanced computer algorithms can struggle with the nuanced task of spotting these faint, moving specks. especially when they are partially hidden by image artifacts or bright star glare. This is where human intuition shines. The Backyard Worlds project presents volunteers with short, side-by-side animations or flipbooks of small patches of the sky. Your job is to look for anything that moves in a straight line against the static star field. It feels less like complex science and more like a cosmic game of spot the difference, or watching for a tiny bug crawling across a detailed tapestry. The thrill is real because you are looking at raw, unprocessed telescope data that no one has scrutinized in this way before. You could be the first person in history to lay eyes on a new world drifting through the void. And people have done exactly that. The project boasts a long list of discoveries credited to citizen scientists, from retired teachers to high school students to graphic designers. One volunteer, for instance, identified a previously unknown brown dwarf system just over 100 light-years away, a pair of failed stars circling each other in a slow dance. Another spotted a remarkably cold, ancient brown dwarf with a temperature barely above that of a summer day on Earth. These are not just names added to a catalogue, they are new characters introduced to our map of the solar neighborhood, each with its own story to tell. This collaborative model has proven so powerful that it has expanded into other projects like Disk Detective, where users search for the dusty disks around young stars where planets are being born. What makes this so profound is the democratization of discovery. It breaks down the ivory tower, transforming cosmic exploration from a distant academic pursuit into a shared human endeavor. It reminds us that the universe is not just for those with a PhD, and access to a giant telescope. It is for anyone willing to look, to wonder, and to contribute a few moments of their attention to the grand puzzle. Every time a volunteer flags a moving dot, they are not just performing a task, they are participating in a centuries-old tradition of looking up and asking, "What is that?" And sometimes they are the ones who find the answer. The idea of life clinging to a world without a sun sounds like pure science fiction, yet it forces us to confront the very definition of a habitable zone. We have long assumed life requires a star like our own, a stable source of light and warmth at just the right distance. But what if the energy source is not a distant fusion reactor in the sky, but a much closer, more intimate force, the relentless pull of gravity itself? This is the speculative frontier of astrobiology, and it shifts our gaze from sunlit planets to the dark, wandering nomads we have been discussing. While the atmosphere of a brown dwarf or rogue planet itself is almost certainly a hellscape of extreme pressures and exotic, toxic chemistry, there is another possibility. Could a moon orbiting one of these free-floating giants become an oasis in the interstellar dark? The concept hinges on tidal heating. We see this in our own solar system. Jupiter's moon, Io, is the most volcanically active body we know, not because of the sun's warmth, but because of the gravitational tug of war between Jupiter and its other large moons. This constant, rhythmic flexing generates immense internal friction and heat. Now picture a similar moon, but one orbiting a rogue planetary mass object, perhaps a world with 10 times the mass of Jupiter, drifting alone through the galaxy. The gravitational relationship between this giant and its large moon would be even more intense, especially if other moons were present to create a complex orbital dance. This tidal energy could maintain a vast global ocean of liquid water beneath a thick, icy crust, even with no star in the sky. The heat source would be internal, geologic, rising from the moon's core. In such a scenario, the surface would be a frozen wasteland, but below, in a sunless sea, the conditions for chemistry and perhaps even biology could persist for billions of years. The energy to drive an ecosystem would not come from photosynthesis, but from chemosynthesis, the process used by life forms at the deep sea vents on Earth, which thrive on chemical energy from the planet's interior. This subsurface ocean would be completely isolated from the hostile surface and the vacuum of space, protected by a kilometers-thick ceiling of ice. but could such a moon even have an atmosphere? It is a profound challenge. With no stellar wind or light pressure and with surface temperatures near absolute zero, most gases would freeze solid. However, models suggest a fascinating possibility: a steam atmosphere. If the tidal heating was strong enough to partially melt the icy crust from below, creating geysers or cryovolcanoes that erupt water vapor and other gases, a thin, temporary atmosphere could form. It would be a dynamic, leaking envelope, constantly freezing out and being replenished by geological activity, a faint, ghostly shroud around an ice-covered world. The challenges to life here are, of course, monumental. The energy budget would be extremely low compared to a sunlit planet. Nutrients would be limited to what was locked in the moon's original composition or delivered by rare comet impacts eons ago. The ecosystem, if it existed, would be slow, sparse, and utterly alien. Yet, the sheer number of these nomadic systems suggested by our surveys makes the thought experiment irresistible. If only a tiny fraction of the billions of rogue planets have large, water-rich moons, and if only a fraction of those experience significant tidal heating, the galaxy could still contain more of these dark ocean worlds than all the Earth-like planets orbiting suns. This radically expands the potential real estate for life in the cosmos. It tells us that we must look not just for planets in the familiar Goldilocks zone of stars, but for any world with a source of persistent internal energy and the right chemistry. The search for life becomes a search for heat and liquid wherever it may hide, even in the perpetual night between the stars. The sheer number of these hidden worlds is almost beyond comprehension. For every star you see in the night sky, there could be another invisible companion drifting in the dark. Current estimates from gravitational microlensing surveys paint a staggering picture of our galaxy's true population. The Milky Way is home to roughly 100 billion stars, a number that has always defined the scale of our cosmic neighborhood. But groundbreaking research now suggests there may be an equal or even greater number of free-floating planetary mass objects wandering between those stars. Think about that for a moment. The number of sunless worlds could rival the number of suns. This revelation comes not from seeing all these objects directly, but from listening to the subtle whispers of their collective gravity. Microlensing surveys, like those conducted by the optical gravitational lensing experiment, monitor hundreds of millions of stars in the dense central bulge of our galaxy, watching for those brief, telltale brightenings. Each tiny flash is a clue, a statistical data point. By analyzing how often these events occur and how long they last, astronomers can build a mathematical model of the invisible masses causing them. The results are clear and humbling. These models infer that for every star in the Milky Way, there could be multiple rogue planets, with some studies suggesting an average of 2 or more per star. When you do that math, the total soars into the hundreds of billions. These are not all giant worlds like Jupiter. The census includes a vast range, from Neptune-sized bodies down to objects perhaps as small as Mars, all cast adrift. This changes the fundamental architecture of our galaxy from a simple map of stars to a far denser, more dynamic sea of dark matter in its most literal form, actual massive objects we cannot easily see. The interstellar medium is not empty. It is filled with these countless nomadic worlds, a vast, drifting archipelago of frozen or temperate islands, silently passing within a few light years of every star system, including our own. This hidden majority forces us to reconsider what a typical celestial body in the universe actually is. It may not be a brilliant, burning star, but a cold, dark wanderer forever journeying through the endless night. Beyond the exotic clouds and faint heat, these cosmic underachievers hold one more spectacular secret. They can possess magnetic personalities of staggering power. While a brown dwarf may have failed at nuclear fusion, its interior is still a churning, superheated soup of electrically conductive fluids, primarily hydrogen under such immense pressure that it behaves like a liquid metal. This roiling interior, combined with the object's rapid rotation, acts like a colossal dynamo, generating magnetic fields that can dwarf those of our solar system's planets. Some brown dwarfs have magnetic fields thousands of times stronger than Earth's, and even rival or surpass the intense field of Jupiter, the solar system's champion. We do not see these fields directly, of course. Instead, we listen for their effects, just as disturbances in Earth's magnetic field create the shimmering curtains of the aurora borealis. The powerful magnetic fields of brown dwarfs can trap charged particles and accelerate them into the atmosphere, sparking auroras on a monstrous scale. But these are not the gentle green glows we know. Imagine an aurora that wraps the entire world, a permanent, raging storm of light in radio and infrared wavelengths, powered by a magnetic engine of unimaginable strength. We detect these phenomena by tuning our radio telescopes to the right frequency. Astronomers have picked up periodic, pulsing radio emissions from several brown dwarfs, a clear signature of electrons spiraling along powerful magnetic field lines. In a few remarkable cases, like the brown dwarf known as LSRJ 1835+3259, scientists have even detected the specific infrared signature of charged hydrogen molecules in its atmosphere, the smoking gun of ongoing auroral activity. This tells us that despite their cold, dark exteriors, these objects are electrically stormy and magnetically vibrant on the inside. The strength and structure of the magnetic field provide a crucial window into the object's deep interior, revealing details about its rotation, the convection of its material, and its evolutionary age. Furthermore, these bright, predictable radio pulses give astronomers a brilliant new beacon for detection. It means we can find some of these faint objects not just by their dim heat, but by the powerful radio signals they broadcast into the void, adding another instrument to our cosmic listening post and proving that even a failed star can put on a dazzling light show. These powerful magnetic storms are not just a curiosity. They provide a direct link to one of the most exciting frontiers in astronomy, the study of planets orbiting other stars. In the quest to understand distant exoplanets, especially the hot, giant gas worlds we call hot Jupiters, astronomers face a frustrating challenge. These planets are incredibly difficult to observe directly. They are lost in the overwhelming glare of their host stars, like trying to spot a firefly clinging to a lighthouse lens. We can infer their existence through the wobble of a star or the dimming of its light as a planet transits, but getting a clear, detailed look at the planet's own atmosphere is a monumental technical feat. This is where our cosmic underachievers, the brown dwarfs and free-floating planetary mass objects, become absolutely invaluable. They are the universe's gift to exoplanet science, a set of natural, isolated laboratories drifting in the darkness. Think of it this way: a hot Jupiter orbiting perilously close to its star and an isolated brown dwarf of similar mass and temperature are, in many fundamental ways, the same kind of object. They are both massive balls of gas with turbulent, complex atmospheres. The crucial difference is that the brown dwarf has no blinding parent star. It sits alone in the void, allowing our telescopes to stare directly at it to capture its light and to analyze its atmosphere without any interference. This gives us a pristine, unobstructed view of atmospheric physics in action. By studying the detailed infrared spectra of a brown dwarf, we can identify the exact chemical fingerprints of methane, water vapor, and carbon monoxide. We can map the structure of its silicate or iron clouds, measure the speed of its global winds, and observe how its weather patterns change over time. This data is not just a description of one oddball object. It becomes a benchmark, a gold standard for our theoretical models. Scientists use these detailed observations to calibrate and refine the complex computer simulations that try to predict what exoplanet atmospheres should look like. When we then point our telescopes at a real hot Jupiter and manage to extract a faint, messy atmospheric signal from the stellar glare, we can compare that messy data to our clean brown dwarf benchmarks. It allows us to ask, does this exoplanet spectrum show signs of similar clouds? Does its chemistry match what we see in an object of comparable temperature? The brown dwarf provides the answer key. This benchmarking process is revolutionizing our understanding of alien climates. For instance, the patchy cloud structures observed on brown dwarfs like Lumen 16 directly inform models of cloud formation on distant gas giants. The detection of powerful storms and jet streams helps us interpret the mysterious brightness variations seen on some exoplanets, which might be caused by massive, swirling storm systems. Without these free-floating calibration points, our interpretations of exoplanet data would be far more speculative and uncertain. They ground our imagination in hard, observational fact. So, every time we decode the atmosphere of a lonely brown dwarf, we are not just learning about a failed star. We are writing the textbook that will allow us to finally read the stories written in the light of worlds orbiting distant suns. At the very bottom of this cosmic temperature scale, we find the white dwarfs. These are the coldest known brown dwarfs in the universe, objects so frigid they make the icy void of deep space seem almost warm. Their temperatures can range from that of a hot summer day down to below freezing, and the very coldest known examples have atmospheres cooler than the human body. They are, in essence, cosmic refrigerators glowing with only the faintest whisper of residual heat. Detecting them is a monumental feat, as they emit almost no light in the wavelengths our eyes can see. Their discovery was a triumph for the Wide Field Infrared Survey Explorer, or WISE, which scanned the heavens in infrared light. WISE found objects like WISE 0855-0714, a white dwarf with a surface temperature estimated to be between -50 and -10 degrees Fahrenheit. It drifts alone in space, a solitary world with no sun, colder than a winter night in Antarctica. To study such an object in any detail, however, requires the immense power of the James Webb Space Telescope. Webb's instruments can take the incredibly faint infrared glow from a white dwarf and spread it into a detailed spectrum, revealing the chemical makeup of its atmosphere. In these coldest of atmospheres, water vapor condenses into ice clouds. Methane is abundant. The air itself would be a strange, thick soup of gases on the verge of freezing solid. These white dwarfs represent the absolute lower boundary of the brown dwarf sequence, the final fading ember of star-like formation. They are so cold and dim that they blur violently into the realm of giant planets. An old, cold white dwarf and a young, warm rogue planet of similar mass are virtually indistinguishable. This forces a profound question: what lies beyond them? What object is so cold it emits no detectable heat at all? We are likely already finding them without realizing it. The coldest free-floating planetary mass objects, those ejected from their systems billions of years ago, have radiated away all their formation heat. They are dark, frozen marbles adrift in the interstellar medium, completely invisible to any telescope that relies on detecting thermal emission. The only way to find these ultimate nomads is through gravitational microlensing, their mass betraying them only by the way they bend the light of a distant star. This means the true population of the galaxy's darkest, coldest bodies remains a shadowy census, hinting at a universe where the line between a failed star and a lonely planet is not just blurred but erased entirely. The magnetic storms of white dwarfs are just a prelude to the revelations still to come. Our map of this dark population is about to be redrawn by a new generation of eyes, both on the ground and in space, designed to see what has been forever hidden. The next great leap arrives with the Nancy Grace Roman Space Telescope, slated for launch later this decade. While it carries the legacy of the Hubble in its name, its mission is fundamentally different. Roman will conduct a microlensing survey of unprecedented scale, staring at the crowded center of our galaxy for months on end. Where current surveys catch fleeting, chance alignments, Roman will watch with relentless patience, capturing thousands of these gravitational brightening events. This statistical treasure trove will transform our understanding of the free-floating population. It will not just hint at their numbers, it will deliver a precise census telling us the true distribution of masses, from giant worlds down to objects the size of Mars drifting alone in the void. For the first time, we will have a clear demographic picture of the galaxy's nomads, settling the debate on whether they outnumber the stars. But Roman is just one piece of the puzzle. On the ground, a revolution in scale is taking shape. The extremely large telescopes, or ELT, are under construction in the deserts of Chile. These are not merely bigger versions of current telescopes. Their primary mirrors, spanning over 30 meters in diameter, will gather more light than all the major historical telescopes combined. This colossal light-gathering power, paired with advanced adaptive optics, will allow them to do something previously thought impossible: directly image and obtain detailed spectra of rogue planets that are not just young and warm, but middle-aged and cold. Imagine pointing such a telescope at a nearby brown dwarf and seeing not a point of light, but a discernible disk with cloud features and storm systems resolved in stunning detail. The ELTs will turn these faint whispers into high-definition portraits, studying their weather in real time and analyzing the chemistry of their atmospheres with a precision we reserve for planets in our own solar system today. Yet even this may not be the final frontier. To truly understand an alien world, you must go there. The nearest known brown dwarf system, Lumen 16, is just over 6 light-years away. While a physical probe is a dream for the distant future, advanced mission concepts are already on the drawing board. One tantalizing idea is interstellar interferometry. Instead of sending one giant telescope, you send a fleet of smaller, synchronized spacecraft, flying in precise formation across millions of kilometers. By combining their signals, they act as a single virtual telescope with a mirror the size of their separation. This technique could, in theory, generate an image of a rogue planet's surface so detailed we could see continents of cloud, mountain ranges of solidified atmosphere, and the dynamic flow of its alien meteorology. It sounds like science fiction, but the principles are grounded in technology we are already developing for other purposes. Each of these upcoming missions, from Roman's statistical sweep to the ELT's piercing gaze to the speculative interferometers of tomorrow, shares a single goal: to pull the darkest members of our cosmic family into the light. They promise to answer the questions we are only now learning to ask, and undoubtedly to reveal mysteries we have not yet even dreamed of. Peering inside a world with no sun is an act of brilliant deduction. We cannot drill into a brown dwarf or land a probe on a rogue planet to take its internal temperature. Instead, astrophysicists build entire universes inside supercomputers, crafting intricate digital models to simulate the unseen hearts of these objects. This theoretical work is the silent partner to every telescopic observation, a necessary framework for making sense of the faint whispers of light we collect. The core challenge is modeling an environment of extreme pressure and exotic matter that we can never recreate on Earth. At the heart of a substellar object, gravity crushes matter into a state called electron degeneracy. This is not a gas, liquid, or solid as we know them. It is a quantum mechanical soup where electrons are packed so tightly they resist further compression, providing the primary support against total gravitational collapse. The precise behavior of this degenerate matter under different pressures and temperatures is described by something called the equation of state. Getting this equation right is the absolute foundation of any accurate model. A tiny error in calculating how this quantum soup behaves can throw off predictions about the object's size, cooling rate, and ultimate fate by billions of years. Once the interior structure is approximated, theorists must then simulate the dynamic engine that transports heat from the core to the surface. This is not a simple process of conduction like in a metal rod. The interiors of these objects are dominated by violent convection, where vast plumes of superheated material rise, cool, and sink in planet-scale cycles over millions of years. This churning dynamo drives the object's magnetic field and fundamentally controls how quickly it loses its birth heat and fades into the cold. But the greatest complexity often lies in the interface between this churning interior and the observable universe, the atmosphere. Modeling the atmosphere of a brown dwarf or rogue planet is like trying to predict the global weather on a world where the clouds are made of molten minerals and the rain is liquid iron. Scientists must account for the condensation of over a dozen different chemical species as temperatures and pressures change with altitude. A layer of silicate clouds may form, then beneath it, a deck of iron droplet clouds, and below that, perhaps clouds of salt or sulfide compounds. These clouds are not smooth blankets, they are patchy, dynamic, and constantly changing, which dramatically affects the object's brightness and color over time. To make any progress, theory and observation engage in a continuous, iterative dance. An observatory like the James Webb Space Telescope delivers a pristine infrared spectrum of a newly discovered brown dwarf. Theorists then feed that data, the specific signatures of methane, water, and silicate features, into their complex atmospheric models. They adjust parameters, tweak cloud compositions, and alter internal heat flows until their digital simulation produces a synthetic spectrum that matches the real one. When the curves align, it is a moment of profound validation. It means the model's prediction of the interior temperature, the cloud deck heights, and the atmospheric chemistry is likely close to reality. But often, the match is not perfect. The observed spectrum might show a stronger water absorption band than the model predicts. This discrepancy is not a failure, it is a clue. It tells the theorists that their model of convection is perhaps too efficient, or that they have the cloud opacity wrong, or that an unexpected chemical reaction is taking place. They return to their digital universe, refine the physics, and run the simulation again. Each cycle sharpens our understanding, turning a fuzzy infrared dot into a detailed planetary profile. This partnership is how we move from simply detecting these dark wanderers to truly knowing them, inferring the storms in their hearts and the chemistry of their skies from the subtle language of light they emit. The dark wanderers of our galaxy have long escaped the confines of scientific journals to fuel our grandest stories. Science fiction has always reached for the most mysterious corners of the cosmos, and the lonely existence of rogue planets and failed stars provides a perfect canvas for existential drama and adventure. These fictional depictions, while often taking creative liberties, speak to a deep public fascination with the ideas astronomers are now confirming are real. The film Melancholia presents a rogue planet on a collision course with Earth, using it not as a simple disaster trope but as a profound metaphor for depression and inevitable fate. Its looming, beautiful presence in the sky captures the sheer, uncaring scale of the cosmos, mirroring the real emotional weight of a world adrift and unstoppable. On a more action-oriented scale, the Chinese blockbuster The Wandering Earth imagines an entire civilization moving our planet as a rogue spaceship to escape a dying sun, directly playing with the concept of a world becoming untethered from its star. While the engineering is fantastical, the core image of planet as a lone vessel in the dark resonates with the genuine discovery of billions of such nomads. Brown dwarfs, those dim failed stars, often appear in stories as treacherous waypoints or hidden bases. Their faint light and strong gravity wells make them ideal fictional settings for smugglers' havens or perilous navigational hazards in the depths of interstellar space, places where a ship could hide or be tragically crushed. This creative impulse is more than just entertainment, it is a vital feedback loop. Early scientific speculations about cool, star-like objects inspired writers decades before the first brown dwarf was confirmed. Now, each new discovery from telescopes like James Webb feeds back into the creative ecosystem, providing fresh, stranger-than-fiction details for the next generation of storytellers. When an astronomer describes clouds of molten iron on a world with no sun, a screenwriter hears the setting for an unforgettable scene. This cycle is crucial. It transforms raw data into narrative, making the awe and mystery of cosmic exploration accessible to everyone. It reminds us that our drive to map the galaxy is not just about cataloging facts, but about understanding our place within a story that is forever being rewritten, both by the laws of physics and by the limitless reach of human imagination. Deep in the constellation Chameleon, a cosmic infant tells a story that defies simple categories. Its name is OTS-44, and it is one of the youngest and smallest free-floating objects ever discovered, a mere toddler in cosmic terms at around 2 million years old. With an estimated mass of only about 12 times that of Jupiter, it sits tantalizingly close to and likely below the deuterium burning limit. By the strict physics definition, this would make it a planetary mass object, not a brown dwarf. Yet, when astronomers trained powerful telescopes on it, they saw something astonishing, a faint glowing ring of gas and dust encircling it. This is a protoplanetary disk, the very same kind of swirling material that forms planets around newborn stars. The discovery was profound. Here was an object so small and dim it barely qualified as a failed star, yet it possessed the full architectural kit to build its own system of orbiting bodies. The disk around OTS-44 is not a relic, it is an active construction site. Measurements indicate it contains enough material to form a small planetary system, perhaps a collection of Earth-mass rocky worlds or a family of moons. This single observation shattered a long-held assumption. We thought that only true stars, or perhaps the more massive brown dwarfs, could hold onto and nurture such disks. OTS-44 proved that the process of building worlds is not exclusive to stellar giants. It can happen in the faintest glow of the smallest cosmic embers. This transforms our understanding of these nomadic objects. A rogue planet or a tiny brown dwarf is not necessarily a lonely, barren rock. It can be a miniature solar system in its own right, a central anchor for its own family of moons or planets, all born together and destined to wander the galaxy as a single, bound unit. The implications for potential habitats expand dramatically. If such a low-mass object can have a disk, then the tidal heating we discussed earlier is not the only path to creating a world with liquid water. A large moon forming within that disk could be born with a warm, watery composition, a ready-made ocean world from the very beginning, forever orbiting its dim parent in perpetual twilight. OTS-44 is a perfect microcosm of the classification struggle. Is it a low-mass brown dwarf that formed like a star, or a super-sized rogue planet that formed in isolation? Its disk argues for a star-like formation, a direct collapse from a tiny cloud fragment, yet its mass places it firmly in the planetary regime. It embodies the blurred line, a living example of why astronomers argue over definitions. It forces us to ask, when does a forming object stop being a star system and start being a planetary system? The answer, as OTS-44 shows, is that nature does not care for our categories. It simply builds, following the same physical processes across an incredible range of scales, from brilliant suns to faint, drifting cinders, each capable of crafting its own miniature cosmos in the dark. This elegant cosmic trick relies on one of the universe's most fundamental forces. Gravitational lensing is a direct consequence of Einstein's theory of general relativity, which tells us that mass warps the very fabric of space-time. Think of space as a vast, taut rubber sheet. Place a heavy bowling ball on that sheet, and it creates a deep dimple. Now, roll a marble past the bowling ball, and its path will curve inward following the contour of the dimple. Light behaves in exactly the same way. Even though it has no mass, a beam of light traveling through space will follow the curves created by massive objects. When a dark, massive object like a rogue planet drifts directly between Earth and a much more distant star, its gravity creates one of these dimples in space-time. The light from the background star traveling toward us must pass through this warped region. As it does, the paths of the light rays are bent and focused, much like a magnifying glass focuses sunlight. From our vantage point, the star appears to brighten temporarily. This is a microlensing event. The entire process is a perfect alignment of cosmic geometry, requiring the lensing object, the source star, and our telescope to be in an almost perfect straight line. Because everything in the galaxy is in constant motion, these alignments are fleeting. The brightening event might last for only a few days or even just a few hours for a very low mass object before the alignment is lost and the star returns to its normal brightness. The beauty of this technique is its democracy. It does not care if the lensing object is hot or cold, young or old, glowing or completely dark. It only cares about mass. This makes it the only method we have for detecting the ancient, frozen rogue planets that have radiated away all their heat and are utterly invisible to even our most powerful infrared telescopes. The data from such an event is plotted as a light curve, a simple graph showing the star's brightness over time. That curve is a treasure map. Its shape is not random. It holds the secrets of the invisible lens. The duration of the brightening tells us about the lensing object's mass. A more massive object creates a wider, longer-lasting warp and thus a longer event. The precise symmetry and peak of the curve give clues about the alignment and can even reveal if the dark object has its own moon, causing a tiny secondary blip in the data. By combining this light curve data with other surveys that measure the apparent motion of stars, astronomers can even estimate the distance to the lensing object. It is a breathtaking feat of cosmic deduction, using the bending of light from a star thousands of light years away to weigh a dark, frozen world drifting silently in the interstellar void, proving that even the darkest matter in our galaxy can cast a shadow made of light. The faint, bending light of a microlensing event points to a deeper cosmic mystery. For decades, astronomers have known that most of the matter in the universe is invisible. We call this shadow stuff dark matter. It does not emit, absorb, or reflect light, yet its gravitational pull is undeniable, holding galaxies together and sculpting the large-scale structure of the cosmos. In the 1990s, a fascinating and provocative idea emerged. Could a portion of this missing mass be made of ordinary matter, just hidden in plain sight? The hypothesis centered on a specific candidate, massive compact halo objects or MACHO. The theory suggested that our galaxy's vast spherical dark matter halo, the invisible cocoon surrounding the Milky Way's bright disk, might be filled not with exotic particles, but with countless failed stars and rogue planets, exactly the kind of substellar objects we have been exploring. These MACHO would be made of normal protons and neutrons, the same baryonic matter that makes up stars, planets, and us. They would simply be too dark and distant to see directly. It was an elegant and compelling thought that the solution to one of physics' greatest puzzles might be a vast archipelago of frozen, sunless worlds. To test this, astronomers launched ambitious microlensing surveys like the MACHO project and the EROS survey. They spent years monitoring millions of stars in the Large Magellanic Cloud, a small satellite galaxy of our own, watching for the characteristic brightening that would signal a dark, massive object in our galactic halo passing in front of them. The results, however, delivered a clear verdict. While these surveys did detect a handful of microlensing events, proving that some such objects do exist in the halo, the number was far too low. These failed stars and rogue planets could only account for a tiny fraction, perhaps less than 20%, of the total dark matter needed to explain the galaxy's rotation and gravity. The mysterious substance holding the cosmos together could not be made primarily of MACHO. The search for dark matter had to turn elsewhere, toward more exotic, non-baryonic particles like WIMP, weakly interacting massive particles. Yet this conclusion, while definitive, holds a fascinating nuance. It did not eliminate these objects, it simply counted them. The microlensing surveys confirmed that a population of dark, baryonic wanderers does inhabit the galactic halo. They are real and they are massive. They just are not numerous enough to solve the primary dark matter puzzle. This means that while they are not the dominant form of dark matter, they absolutely represent a significant form of normal matter that has been hiding from our view, a kind of baryonic dark matter. Our galaxy's inventory of ordinary stuff, the atoms that build everything we see, was missing a major entry. We now know that entry is a sprawling population of cold, faint objects drifting in the galactic outskirts. So, the search for dark matter led us, ironically, to a profound census of our own cosmic backyard, revealing that a portion of the universe's shadow is cast not by unknown physics, but by the cold, dark forms of countless forgotten worlds. These cosmic underachievers are not just subjects of research, they are becoming some of our most powerful teachers. In classrooms and planetariums around the world, brown dwarfs and rogue planets are emerging as perfect, engaging tools to unlock the fundamentals of the universe. Their story is a masterclass in physics packaged in a single, fascinating object. Take the concept of nuclear fusion thresholds. Explaining why our sun shines is one thing, but demonstrating the precise line where that fire fails makes the physics tangible. A brown dwarf embodies that exact boundary, a cosmic, almost, that visually defines the minimum mass needed to ignite even the faintest nuclear spark. This makes abstract equations about pressure, temperature, and mass suddenly concrete. They also revolutionize how we teach stellar evolution. The classic Hertzsprung-Russell diagram, that foundational graph plotting stars by brightness and color, used to have a glaring blank space in its lower right corner, a realm of faint, cool objects that theory predicted but we had never seen. The discovery of brown dwarfs filled that void, literally completing the diagram. Now, educators can point to that corner and show real data points with names like Lumen 16 or WISE 0855, proving that our maps of the cosmos are living documents, constantly being redrawn by discovery. Their alien atmospheres serve as thrilling laboratories for chemistry and meteorology. Discussing cloud formation becomes far more captivating when the clouds are made of molten sand or hot iron droplets. The violent weather on these worlds illustrates fluid dynamics and heat transport on a planetary scale, showing physics in action under extreme conditions we could never replicate on Earth. Most importantly, they teach a vital lesson about the scientific process itself, the ongoing debate over classification. Is it a failed star or a rogue planet? Presenting this active controversy to students demonstrates that science is not a set of fixed answers in a textbook, but a dynamic, sometimes messy, human endeavor to categorize a universe that delights in defying our boxes. Planetariums have seized on this narrative power. Modern shows now take audiences on journeys to the twilight worlds of brown dwarfs, using stunning visualizations based on real telescope data to fly through their turbulent, layered atmospheres. Science channels and documentaries feature them as the hidden monsters of our galactic neighborhood, bridging the gap between familiar planets and distant stars. By focusing on these mysterious in-between objects, educators can pull the public directly to the cutting edge. You are not learning century-old facts. You are exploring the same questions that astronomers are grappling with today, using the same tools like data from the James Webb Space Telescope that are making headlines. This transforms passive learning into active participation, inviting everyone to look at the night sky and wonder not just about the bright points of light, but about the profound and populous darkness in between. The legal and ethical map of space dissolves in the profound darkness between stars. For decades, our cosmic laws have been built around familiar landmarks, like the Outer Space Treaty, which prohibits nations from claiming sovereignty over celestial bodies like the Moon or Mars. But this framework assumes those bodies orbit a star within a defined system. A rogue planet, by its very nature, defies this geography. It is a sovereign world of nothing, orbiting the galactic center along a path that may never bring it near another star, let alone a human outpost. So, if a future generation builds a generation ship and, after centuries of travel, settles on a wandering world with a subsurface ocean, who does it belong to? The crew who landed there, the nation or corporation that funded the expedition? Or does it remain, as our highest ideals suggest, the common heritage of all humanity, even if that humanity is dozens of light years away? This is not idle speculation. The sheer abundance of these nomads means they are the most likely first destinations for any civilization stepping beyond its own solar system. They are way stations and potential resources scattered across the galactic ocean. Their value is incalculable. A brown dwarf, for instance, is not just a failed star, it is a vast reservoir of primordial hydrogen and helium, the very fuel needed for advanced fusion propulsion. Future ships might not carry all their fuel for a millennia-long journey. They might plot courses that swing past these dim objects, using their gravity for a slingshot and skimming their atmospheres for fuel to power the next leg. This turns a cosmic underachiever into a galactic gas station, but the ethics of extraction are fraught. Would harvesting a brown dwarf's atmosphere to power a human fleet constitute harm? Is it mining, or is it a form of cosmic landscaping on an unimaginable scale? The questions grow more intimate with a rogue planet. If one harbors a hidden, tidally heated ocean beneath its ice, does that ocean belong to us if we find it? Do we have the right to drill through the ice to introduce our probes and potentially our biology into an ecosystem that has evolved in total isolation for billions of years? The prime directive from science fiction becomes a pressing practical concern. Our history on Earth is a chronicle of exploration followed by exploitation, of seeing new lands as terra nullius, empty land free for the taking. The galaxy's nomads are the ultimate empty lands, and they present us with a profound test. Will we repeat our old patterns on a galactic stage, or will we evolve a new ethic for a universe that offers not just new territories, but entirely new categories of world? This is the true legacy of discovering this hidden population. It forces us to look centuries ahead, to see that our greatest challenge may not be the physics of interstellar travel, but the wisdom to navigate the moral void it opens. Every faint infrared dot on an astronomer's screen is a future crossroads, a question waiting for an answer from a humanity that has learned to see in the dark. The cosmos is not a simple map of bright stars and orbiting planets. It is a rich, layered tapestry, and its most numerous threads are woven from darkness. Our journey has revealed the true nature of substellar objects, the cosmic in-betweeners that defy our old categories. They are defined by a single, silent boundary, the deuterium burning limit at 13 Jupiter masses. Above this line, brown dwarfs flicker with brief nuclear fire, failed stars with alien weather of molten rock. Below it, a vast diaspora of rogue planets and planetary mass objects wander forever dark, their only warmth a fading memory of birth. This hidden architecture challenges everything. It forces us to see planet and star formation not as separate stories, but as a continuous spectrum of creation, where a tiny collapsing cloud can build its own miniature solar system, and where violent young planetary systems routinely cast their giants adrift. By studying these cosmic underachievers, we are not just cataloging curiosities. We are decoding the atmospheric chemistry of distant exoplanets, calibrating our models of alien climates, and taking a true census of the normal matter in our galaxy. They teach us that the universe is far more inventive and populous than we ever dreamed. So the next time you look up at the night sky, remember this. For every point of light you see, there are countless unseen worlds drifting in the profound dark between them, an archipelago of frozen or temperate islands on an endless journey. These nomads are the silent majority of our galaxy, and their story is still being written. What do you think awaits us in that darkness? Share your thoughts on these cosmic mysteries in the comments below, and subscribe to join us on the next journey into the science of tomorrow.